Hi, good morning all. This is Vishal Singhal from Selfstrat, your host for today. So we have Mr. Blaine Bateman from US. He leads EAF consulting in business analytics of machine learning, strategy, and market analysis. With 35 years plus international experience, he graduated with special honors from chemical engineering and later certification in quality management. I think Curtin University, Boulder uh, and machine learning from Stanford through Coursera. And experience includes U.S. government R&D, several startups, and 13 years with Laird as global VP marketing and others. Statistics, machine learning, electronics, automotive, antennas, oblique RF, strategy, business development, and product development with 18 patents in instrumentation and antennas and RF design. Over to you, Blaine. Thank you for the webinar delivery time. Hope
Okay,
it will be a good one, and people will be joining in while you are on. So please
sure.
go ahead. Thank you.
Okay, great. Well, thank you for the introduction. And so, yes, again, I'm Blaine, and I'm based in Colorado in the US. Um, and I've been consulting for a number of years, and the last 5 or 6 years focused on machine learning and data science. And I'm going to give an example of a particular piece of a project I thought would be interesting to everyone this evening. So the topic has to do with over-the-road diesel trucks, and there are a lot of regulations around the emissions from diesel engines, both the trucks as well as stationary ones. And there's very complex systems on most of these trucks. There's as shown in this illustration. So you start with exhaust coming from the engine on the left. You go through a whole series of different units. And the thing I'm going to talk about tonight is the one sort of towards the right. This is copper zeolite SCR, and SCR stands for selective catalytic reduction. And the job of this unit is to convert nitrogen oxides to nitrogen. So it's reducing the NOx to N2. There are a bunch of sensors and other things in these systems, and I'm going to focus on what's going on in that blue section towards the end. On the right, it's just a little bit about what's going on. Basically, inside of there's a solid catalyst that is typically a ceramic with some kind of metal that's been applied to it. And the idea is to provide sites, which are denoted by the S1, as places where ammonia can absorb. The ammonia gets into the system by being injected as urea and water. That's shown in the middle of the picture. Also known as diesel exhaust fluid, which is kind of a funny name. But so you inject urea, and at the high temperatures in the exhaust, it converts to ammonia. The ammonia adsorbs onto the surface of the catalyst, and there's various equilibrium constants and rate constants associated with that adsorption and desorption. But once it's adsorbed, the ammonia can react with the NOx and reduce it to nitrogen. So basically, we're trying to control this catalyst, and we need to know the state of it so we know whether we need to add more urea or less urea, because we don't want to end up sending ammonia out the exhaust, and we don't want to send NOx out, so we need enough urea but not too much. So I'm going to describe a way that we can monitor this as a sensor and control it, and how that ends up being a machine learning problem. So in this slide, the section of the exhaust system, so if I go back 1 second, again, where it says the copper zeolite SCR, so that's a big metal tube, basically, with a catalyst inside of it. So that's represented here on the right by these cylinder sections. And we can look at that tube as a metal cylinder, which is like a cavity. and we can inject radio frequency energy at different frequencies, and the radio frequency energy can resonate. And on the right, we're showing two different frequencies where it's resonating, and depending upon the frequency, the energy in the cavity is in different places, and so the part of the catalyst that it actually is sensing depends on the frequency. It's also very temperature dependent, but the main thing that we're interested in is that on the left you see a section of a frequency spectrum where in the pictures on the right, those two lines coming in are antennas. They were putting in and taking out the radio frequency energy. And on the left is basically the signal measured between those two antennas. And you can see peaks, and that's where the resonances are. And so the frequency 1 and frequency 2 might be these two middle ones, which are labeled B and C in that chart. And the thing that's interesting is that when there's no urea, so there's no ammonia, the peaks are typically a little higher and maybe a little bit to the right. And when you add ammonia, they can shift. And they don't always shift exactly the same direction and the same magnitude. It depends on the frequency and the temperature and the amount of ammonia. But that signal change in the radio frequency, we can measure that. So down below, I zoom in on two features. So we can measure the difference between the blue and the orange. And we can do that with basically a radio frequency sensor. And in practice, we have a whole bunch of these resonances we can observe. So in the data I'm going to show you, in the actual system that we're measuring, we look at about 25 different frequencies. So you can have a measure of the change in the signal at 25 different points across the frequency spectrum. So each one of those becomes a feature. So that's where we start with the machine learning. It's a very complex nonlinear phenomenon, and it's very difficult to apply a simple linear or polynomial fit to get a good calibration of the sensor. However, machine learning is really well suited to this. The challenge is that if I look at our data, and I mentioned we have 25 frequencies, at each frequency we can measure the size of that peak and the width of the peak, and we can also measure a couple of other RF properties. So we actually have 2 or 3 values at every of those 25 frequencies. So on this chart, I'm showing about 50 features that are basically the values that are going into the machine learning model. And this chart basically is showing a set of data that's collected over a calibration run. And the challenge is you can see that the different features behave differently. And we know that there's noise. We know there's measurement problems. It's a very noisy system with the engine running. You have vibrations, you have changes in flow, temperature fluctuations. So we know that there are noise, and we'd like to get the best training data set as possible. But when you look at these data, in this case, there's no obvious way to say, oh, here are the outliers that we could remove to improve our data set. And in the real data set, in addition to the 3 values per frequency times 25, we also have temperatures, sometimes some polynomial temperature features, maybe a flow rate feature. So we have on the order of 100 of these features, and we're trying to improve the training data set by trying to find outliers. So now I'm going to describe how we can go about doing that. The traditional way to do outlier detection is you do something like in the scikit-learn, there's the so-called local outlier factor. And the LOF is basically looking at the density in regions in the data set and trying to find points that seem abnormal compared to the local density. That's why it's called local outlier factor. A challenge with the LOF is you have to prejudge the concentration of outliers. So in this case, I actually worked backwards. I had a number in this data set. The data set I'm showing you has about 25,000 rows times 100 features. And we found a little less than 1,000 outliers using the method I'm going to show. So we can go back and we can put that number in and say, okay, we expect maybe around 1,000 out of 25,000 outliers, and give it to the LOF function and have it fit it, and we can then extract the outliers. And so we would just collect their the index values so we can plot them later. So this is the traditional way that people would do it with a standard tool like scikit-learn. Now, I want to take a small detour and explain about UMAP, and then I will show how we can use that to go about this in a different way. So UMAP is a dimensionality reduction technique, and you might have heard of UMAP, you might have heard of TS&E, you might be familiar with principal components analysis. All of those methods can take a high dimensional data set and shrink it into a smaller number of dimensions, but they work in very, very different ways. And the way UMAP works is it essentially assumes there's some distribution in the data, and then you recursively fit that distribution in a lower dimensional space. And the mathematics isn't that critical, but essentially you are making a statistical assumption and then fitting backwards into the low dimensional space to find the low dimensional manifold. It turns out when you do that, the manifold, the low dimensional space, is locally connected and has a lot of nice statistical properties. So people discovered that UMAP was very useful for finding latent lower dimensional spaces in high dimensional data. You might have heard that, for instance, that UMAP is nice because it's non-parametric compared to TS&E, where you need to tune it. And that's actually not true, and I'll show you that. In general, I find UMAP to be a little more user-friendly and a little better behaved, but TS&E could be used for the similar purpose as to what I'm going to show you, or even some simpler dimensionality reduction technique. But UMAP has nice properties, so I decided to try and apply it in this project, and the results were good, so I thought it was interesting to show that. So if we take UMAP, I'm going to start with the simple application before I talk about outliers. On the left, that's basically all the code you need to take a data set and compress it into, in this case, 2 dimensions. These data are the traditional MNIST, which is the handwritten digits classification data set. So you're probably familiar with this in many cases. So on the right, we see the output of this, where we fit the UMAP manifold in 2 dimensions. And you notice that I have to give it a parameter for the number of neighbors and a distance parameter. There are defaults for these in UMAP, and sometimes in a tutorial, it might look like there's no parameters, but the reason is the defaults work fairly well. But in a real case, you have to adjust these to optimize the results. And when I show you the outlier detection, I've made some small changes to those values. But with those values, so, and of course we fix the random state just like other algorithms, where if we want to get the same result twice, when we have random initialization, we set the random state. So with that line of code, we define the mapping function, then we fit the mapping function, and then we can transform the data from n dimensions to 2. So in this case, with the MNIST, these data are black and white digitized handwritten digits, and when they're flattened out, they're 784 dimensions wide. So this data set is 60,000 rows by 784 dimensions, and UMAP, without knowing anything about the data, compresses it and finds 10 clusters which line up with the digits extremely well. So that shows the power of UMAP, and you could probably get a similar result with TS&E with a little bit of tuning. The reason I show you this is to be able to contrast with what we can do with it for outlier detection. So we run this, we get these clusters, and we could actually look at these clusters, and we could see maybe there's a few points on the outside of them, and we could think about trying to find a way to go in and find the cluster centers and look at outliers in the local space. But we can go about this in a simpler way. Now I want to introduce them with the UMAP. There is another parameter, this called op mix ratio, and the default value is around 0.5, and when you make the value really small, you reduce the tendency to keep as much of the local structure. What you see on the right is we get a very similar result, except there's more outliers around all of those clusters. So it turns out if you read the UMAP documentation and you read up on the theory, setting that ratio to a small value is more optimal for outlier detection. Setting it to a larger value is more optimal for just finding clusters and structure. So that's another case where I mentioned earlier, it really is not parameter free. So that is an adjustable parameter. And in the data I'm going to show you this applied to, that I showed an example of earlier, I did some testing and I found that setting it to a very small value was best. So you can see, obviously, we have the ability with UMAP to capture that a lot of the data are very similar in each digit, but in each case, there are some that are different. And I won't go through what all this looks like on the UMAP documentation. They have some more charts, but it's quite interesting. It can find the fact that some digits are drawn with very thick lines or some digits are drawn crooked. This is all without knowing anything about the data. So it's, from that point of view, it is unsupervised, that it can find the structure and find the outliers without being told anything in particular other than these parameters of the number of neighbors and the distance parameter for the local characteristic. So this gives you an idea of what UMAP can do, and that it might be useful for outlier detection. So if I take a step back then and I say, well, what does it look like if I take the data I showed earlier, where I have about 100 dimensions, and I apply UMAP to it, and I ask it for now 3 dimensions instead of 2, I get a cloud like this. And this is this cloud has been sampled so you can sort of see more of the structure. So there's not 25,000 points in there. But what you see in this case is we get sort of a big cloud, and it's a little hard to see the 3D structure, but I'll show you some animations later so you can really see it. But this is a 3-dimensional volume, and the points are distributed in it. And in fact, the colors, these are color coded by the average temperature in the test system. And remember, we're in an exhaust system, so the tests were run at different conditions, and the exhaust gets hotter or colder, anywhere from 200 centigrade up to over 400 centigrade. So the colors show that there is some separation with temperature, but temperature, even though it's an obvious variable, is not sufficient to separate all of the data. When I got to this point, I was interested in how I might detect points that are sort of outside a 3-dimensional volume that was defined by this cloud. I'll show you how I can go about that. Before we do that, one of the things to keep in mind is that I showed you earlier that the traditional method for outlier detection might be using something like local outlier factor. We can apply that same algorithm to the embedding. So if you keep this in your mind, I'll go back one slide. So here we've taken the 100 dimensions, put them into 3-dimensional space. So each of the points in this space now has 3 values associated with it. So we've compressed it into a low dimensional space of 3 dimensions. So here on the right, I can take the embedding, which has 3 components, X, Y, and Z. I can put that into the local outlier fit algorithm and find the outliers that way. So that's one approach so that I could apply UMAP to get the outliers. If I do that, I get something that looks like this. And what you see, and this cloud is a little less sampled, so it's a little more dense. But what you see is that the purple points, these are the ones I've now, I took all those values found by the LOF algorithm and colored all of the ones that LOF found as outliers purple, so they would stand out. So what you see is, we still see the structure we had before where we have sort of groups by temperature, but the outliers that it's found are mostly within this volume. So I wasn't completely satisfied with that result, and I wasn't seeing the improvement in the model, the machine learning model I was looking for, because remember that our goal when we started is we're trying to feed these data into a machine learning model to learn the behavior of the radio frequency response with the amount of ammonia. And when I applied this method, I wasn't seeing a lot of improvement. We can there's 2 ways we can use the LOF. The one I just described, and I actually had the slides flipped, so I apologize for that. So what I just described, where I've applied the local outlier factor to the embedding, again, you see the cluster, the structure we had before, and inside we see a lot of the purple or pink points. If I apply the local outlier factor, I showed the equation in the beginning where we just applied it to the raw data, but I visualize it in the embedded space, we see that the points it's finding, even from the raw data, are very similar to the points LOF finds in the embedding, which is here. So we don't see a huge change there. So in neither case, using local outlier factor on its own or using local outlier factor on the low dimensional embedded space, I wasn't seeing the improvement I wanted. It doesn't mean that in some ways these are not outliers, but again, my goal is to get the best training data set, and I wasn't seeing the improvement in the model that I was hoping for, given that I believe there's noise in the system. We'd like to find outliers we can remove. So the next approach I took was I said, we have a 3-dimensional space, and in this case, although there is some structure by the temperature, we can see that. Generally, we have a single 3-dimensional ellipsoidal volume, which you could otherwise look at as an egg shape, if you will, in 3 dimensions. So I asked the question, if I could fit a volume to this cloud, could I then threshold points that are inside or outside of a shell and look at those as outliers? So the next problem I had was, now I have my data. I've embedded it into a 3-dimensional space, which I can visualize. How do I fit a surface to it that makes sense? And this is where I like to say that in the spirit of half the things or more that we want to do have already been done, and you can find them on the internet. a little bit of searching, and I found a person who had already solved fitting the three-dimensional ellipsoid using a least squares algorithm. And so I used this reference and I borrowed this code. And by the way, the links here for the source are in the code that I'll show you, which is on GitHub. So if you want to go look this up, you don't have to memorize that. It's in the code, because I always give credit if I borrow something. So I found this code, and it turns out this problem is not completely trivial. There are a lot of different ways to solve it, but I took an algorithm that was available. I adapted it for my purpose, and I fit it. And then I said, now that I have a three-dimensional ellipsoid, I can define essentially a radius, and I can say the points outside the radius are outliers. I could also say the points inside of a certain radius could be low outliers as well. So in this diagram, we have the same data I had before, except that now the points that I've labeled are the points that are outside a threshold, essentially a radius parameter of 0.5, compared to the least squares fit of this volume as a three-dimensional ellipsoid. So I just want to show you, let's see if I can get this to work. So now you can see the three-dimensional character. It's easier to see that all of these points are lying around the perimeter, because that's how I've defined it. And you do see that as it rotates, you can sort of visualize that they are kind of outside of a surface that contains most of the data. Just to show how it varies, this threshold parameter now becomes another adjustable parameter. So that becomes a hyperparameter that I need to optimize. And if I change that and make it smaller, we see more points that are now defined as outliers. So with this method in hand, I then just optimized for the radius threshold, and was able to get percent level improvements in the machine learning model performance by excluding outliers at a certain threshold. So by using the fact that UMAP can put my data into a low dimensional space, and then I can use some math to fit a surface around that space and look for things that are seemingly odd, I achieved a very beneficial result. And when I say I got percent level improvements, what I mean is I filter the outliers from the training data, but not from the test or validation data. And the percent level improvements are on the validation and test data. So it did prove to be effective to find and remove points that were degrading the training of the model. Now I'd like to shift gears and actually go through a little bit of the code. It's relatively simple, and everything I'm going to show you is on GitHub, so you can go get it and play with it, including this sample data set, by the way. So that, because these are real data, which is sometimes more interesting than a toy data set. So let me...
Audience, any questions before he moves on to the code?
Yeah, thanks, Vishal. I've been watching the chat box. I haven't seen anything pop in just yet.
Yeah, so if you have any questions before he moves on to the code, that will be great. Otherwise, it may be difficult to switch in between. So go ahead. I think telecom is I would say this is probably the first telecom related data set webinar we are having. So people are taking time to absorb.
Yeah,
Yeah,
it's a lot to absorb, actually. So it's,
yeah.
say, fortunately, I'm providing all the code so people can play with it. So now you should be seeing my Jupyter notebook. Is that true?
I'm sorry, yeah. Go ahead.
Okay, great. All right, so I'll keep going. So it's relatively simple what I'm going to show you. Basically, for UMAP, you need to install and import UMAP in Python. There is the ability, which I'll show you, to not only plot the reduced dimensional space, but also look at the connectivity like a network diagram. I'll show you that just as an aside, because it might be of interest to people. If you want to do that, you need the plot function. Matplotlib, etc. That's all very standard. I'm using a linear algebra library from NumPy to get a couple things for the ellipsoidal fit. A little bit of scaling stuff here, the local outlier factor I mentioned earlier, and then this part is Matplotlib just to get the 3D plots. So really, you know, the heavy lifting is UMAP, and then to do the fitting, there's a little bit of linear algebra, and that's really all there is to it. This is the algorithm to do the fit. Here's the link that I mentioned before. It's actually incredibly simple. So basically, it's just doing a least squares fit to a representation of the three-dimensional ellipsoid. And you can basically, you know, solve this into an algebraic representation and then fit that with least squares. I have a couple other utility functions to, if I have an ellipsoid I fit and I want to get the values in XYZ, this function does that for me. And then I have one other function where I translate and center the ellipsoid so that it's easier to do the visualization. So I created this function to do that. So to do the MNIST fit that I showed earlier, the only thing that's additional here is I import the data from TensorFlow Keras. You can get it from a lot of different places. This is convenient because it's already flattened in the 784 dimensional space. So all I have to do is run that piece, and I get I'll get my MNIST data. And then this is, I showed this in the presentation. This is the two-dimensional embedding for the MNIST data. So here I flattened it into this X train, so it's 60,000 by 784. Here I'm going to turn that into 2 dimensions. So I run this. Give me just a second. I want to I'm just trying to get my controls back the way they should be. There we go. So the UMAP is the part that takes a while, so you can see that's running. I just wanted to be able to see that so that we can all see what's going on. And there is, depending on your system, I'm actually running on Windows, but if you run on Linux, you can download a GPU supported UMAP to speed it up a little bit. So what it's doing right now is it's basically fitting the two-dimensional embedding onto the MNIST data. And this will just take another minute or so. And then I'll show you the results.
One offbeat question, Blaine.
Yeah.
From business perspective, where do you think marketeers or people in these companies, the business guys in these companies, can pitch into such a solution? Would you be able to comment on that?
There's a lot of data sets that end up being very high dimensional. You know, even things like natural language processing, you do
Mm-hmm.
vectorization. So
Right.
anywhere you have a situation like that you'd like to see if you could clean the training data to improve it, because even NLP data can have noise in it, because depending upon the source of the raw text.
Okay.
So essentially anything that's tabular high dimensional data, which applies to a lot of machine learning, you could apply this to as a
Okay.
nearly unsupervised way to find outliers and try and improve your model performance.
Got it.
Okay.
Yeah.
Okay. So let me just so people can see it.
Another question is coming.
Okay.
So that's, can a particular UMAP transformation be stored as an object and be used for inference on a test data set and therefore in production?
Yes, because we're fitting the mapping, and just like any other like scikit-learn model. So you can store, and that's what I'm doing here. I'm storing the fitted mapper in an object, and then there's just the transform method. I can apply that to anything. So I could apply it to a new data set as long as that data set was dimensionally similar to what we fitted on. So that's actually a nice advantage of using UMAP this way, because it basically becomes a fit model that you can apply to new data, just like other scikit-learn methods.
So it can directly be used in a production environment.
Yes.
Okay.
Okay. So what I wanted to show here is with the fit embedding. You see, this is the mapping we saw earlier. So that's as simple as that is and how long it takes. So we've fit the MNIST data into 10 clusters, and we apply that to the data set. We see the result here. Now I'm going to run it on the test data, and this data frame here, the UMAP demo data, these are the data I showed in the presentation, and I put this on GitHub, so you can reproduce what I'm showing. And for the normal outlier values, applying the LOF, I'll go ahead and fit that and save it, because I can show that later. So here we're applying this scikit-learn LOF directly to the raw data, which is my the demo data. So it's say roughly 25,000 by 100 dimension data. And I'm just going to store those. One interesting thing I showed in the presentation, that the result applying LOF directly to the raw data and applying it to the embedded data was similar. What's interesting is that as your data dimensionality grows, applying even LOF to the embedded data is much, much faster. So in that sort of production question sense, if you wanted to use just traditional outlier detection, you can still improve that by using UMAP and dramatically speed up then the LOF, because the density function in LOF has to look at every point and try and estimate its local group. So when you drop that from 784 dimensions to 2 or 3, it can be much faster. So you see that took a while to do it on the raw data. In the UMAP, so I've just stored that, and I'll show you that in a minute. In the UMAP section, this is what I showed. We have the 3-dimensional version. And then I'm going to fit a two-dimensional version just so I can show that UMAP provides the ability to look at the connectivity of the low dimensional space, which I thought might be interesting. I'm not using that in this case, but I thought it would be useful for people to see that. So I'm fitting both the two-dimensional and three-dimensional mapper, and then I can apply them to the same data. Let me run this. And this, again, this is the slowest part, but I'll show that I can reuse this here in a second. So let me zoom this back up. It might be easier for people to see.
Audience, any other questions? It's actually great to see so many people coming in early morning attendance. We started these morning sessions India time as an experiment, and people started increasingly coming in.
Yeah,
I
I know
wasn't
it's kind of
expecting so
early.
many.
I know it's kind of early, especially in India. You know, when I worked with people in India and in Asia, it's usually we didn't try to start anything before 9, but
Yeah,
so yeah, it is great to see people getting in and seeing what's going on.
right,
I know you're
right.
recording this so people can watch it again.
Yeah, yeah.
So that's great. Yeah.
So I shared the link with audience on for YouTube. It will be posted in 2-3 days time.
Good. Okay. So again, this is the slowest part. It'll take just another minute or so to finish fitting the UMAP. I wanted to actually do it live so that people could see it work and get an idea of how long it takes. I'm running this on a laptop, so it's not especially powerful. So
Sure.
if you throw more computer power at it, it will go faster. But it's very doable. Is one of the important things. It's UMAP is I think it's fairly scalable and has a lot of uses. So this one was quite interesting to show. So it's finished. The first part, and what it's doing is constructing the two-dimensional network diagram. So that'll finish here in a second. So this isn't that interesting in this particular case, but what's interesting is depending upon what we're looking for. So it's showing the network connectivity of the points in the lower dimensional space, and this is the UMAP data. So it's this is the real data. So it's as we recall, the three-dimensional representation is kind of still a cloud. So there's not a lot of obvious structure here, but depending upon your data set, you can look at this connectivity, and that might be of value to some people. So, and that figure was generated right here by this plot connectivity. So I wanted to demonstrate that. Now remember, before I did this piece, I ran LOF on the raw data, and that took a little while. Now that I have the embedding, I'm going to run it again and save it in a different variable on the embedding, and it's already finished. And that shows the advantage of running, looking for outliers in the embedded space. And what's really interesting is with UMAP, it turns out in many cases to be as effective as finding outliers in the raw data. So this is an interesting way to streamline looking for outliers. This section of code is specific to what I'm doing. I recover the scaling of the temperature data and I color code it. So this isn't really important. This just makes it look nice. So there's no real magic here, but that's just gives me the color coding I was looking for. We could leave that out and plot everything in one color and color the outliers separately, but for my purposes, I color code it. Then one thing in terms of visualization is, in this case, I'm filtering about half of the points out just to speed up the visualization, because in this case I'm using Matplotlib, which is not super fast. If you use another library, like something that's running in Java, you might not need to sample because it might be faster. Matplotlib is not super fast in 3D, so I right here I filter it, and that's when I showed in the presentation. I showed that in some cases I had filtered out some of the points so you could kind of see more of the space in the 3D. So that's where that occurs. But that's purely a random sample. I'm not doing anything with the data. So here I'm creating the 3D plot, and all that really matters is right here. I'm going to do this 3 times. In the code, I have code to plot the outliers using the radius threshold on the embedding. I have code to plot them using the LOF on the raw data and LOF on the UMAP data. So I'm going to show that one first. So we have the embedding. We're applying the LOF algorithm to that, and I'll show that. So we're going to run this.
Another question is there, Blaine.
Yeah.
Is there a way to compute the information loss when we reduce dimensions to UMAP?
That's a good question. I imagine there is a way, but I don't have. I don't recall seeing that explicitly addressed in the UMAP documentation. So it might require some other algorithm. I'm not. I don't have something at my fingertips where I've done that, but obviously there are like entropy measures that you could apply as an estimate. I don't have an, I can't point you to a method right off the top of my head, but I would probably start by looking at whether I could calculate an entropy measure on the on the embedded and the not embedded space. But I don't recall that UMAP has a function to do that on its own, so you'd have to kind of build that yourself.
Sure, else you can contact Blaine on his contact ID he will be sharing towards the end, and you can interact probably.
Yeah, in fact, that's the easiest way to reach me, and you can find me on LinkedIn as well, of course. So
Sure.
this is so we took the we did the UMAP embedding, and then I applied the local outlier factor to the embedded space, and that threshold actually doesn't apply because we're not thresholding. But you can take this and rotate it, and see that most of the points are inside this volume. And that's what I showed earlier. So if I go back and we compare that, and I put all this in here because I thought people, might want to be able to use the code in these different ways. So I went ahead and just left these in. I can quickly rerun it. And this is the same. This is applying the local outlier factor directly to the raw data. And you see it looks extremely similar to what I just showed. And again, things are kind of in the internal. So there may be some information in these outliers, but they were less effective for my purpose of trying to improve the generalization of the model. So the third method is to then assign outliers based on their radius for the fitted ellipsoid. So I'll do that. So now this is at threshold 0.5, and you can see now we're highlighting the points that are out on the edges. And when I did that and filtered my training data that way, is when I saw real improvements. So that is the end of the code piece and the end of everything I wanted to present. Let me I wanted to show one last aspect. When you find the outliers the way I just showed, where I fit the 3D space and then filter points on the outside of the shell. Here the pink again, the pink are the outliers, and all the other colors are the temperatures, similar to before. And what is really interesting is that, again, you can see it would be extremely difficult to a priori find these outliers in any given feature, because in some cases they look very normal, they sort of sit right in the middle of the data. In other cases, there's no real pattern for some of the feature space. So this is a really powerful technique in that it can find things in this lower dimensional space that there's no simple way to find them in the high dimensional space. And that's one of the things that attracted this method to me. And you can see that here, that if you were given the job of find a rule from this chart for how to get the pink ones, it would be extremely difficult to find them all in this high dimensional space. And then I gave you this Gmail. If you use this EAF Pres or my name on GitHub, you'll find my public GitHub, and you'll find this repository there. Under UMAP outlier removal, there's some other public things there you're welcome to peruse. And I'm Blaine Bateman on LinkedIn. So I'm easy to find, and I'm always happy to try and help and give advice if you have questions about anything that I've shown.
Great, thank you, Blaine. Audience, any final questions you may have? And Blaine, I felt it was a good webinar because first it was for high dimensional data. I think this was first of its kind with that last chart that you showed. That looked more modern art to me as a business guy than than the tech guy. So I'll appreciate if you can give more webinars like these. It will be very, very gyan-oriented for a lot of our audience here.
Yeah, absolutely. So I'll work with you on more topics. I'm definitely happy to share, and I look forward to any questions and whatever my next webinar is.
Sure, great. So since no more questions are coming, so we'd like to close it here. And thank you again for joining in early in the morning, and thank you, Blaine, for sparing time to deliver this.
Yeah, and thank
session.
you for your help with the questions as well.
Sure. Thank you, and have a good day ahead.
Bye-bye.
Good night.
Thank you.